Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're dealing with electric circuits. And here we have an electric circuit. Now there's not going to be much wah, 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 no clickety, clickety, click, very little of that. We're going to have fun. So we've set up the circuit. We've got a battery. There's the battery with a negative on top, positive at the bottom. We've got a switch. We're going to use this both for an ammeter and a voltmeter. Now, here we've set it up with a voltmeter to measure across the battery. And the battery has got what is called an internal resistance, that. Now, it's really inside between the negative and positive, but we represent it in science with a little boxy thing with dashed lines, and we put this outside. Just makes it a little bit easier, but that is actually the internal resistance of that cell. So we're going to have a voltmeter and ammeter. We're going to have to substitute those, but it makes no difference if we remove that voltmeter. A voltmeter's got infinite resistance, and it'd be just like if we take it away, it doesn't change the measurements. And in the meantime, we have a wire across that because just like an ammeter, a wire has negligible or no resistance. So are we ready to use our formula? Now this is the most common formula used in matric physics science. EMF equals I R plus R in brackets. EMF. Now what is the EMF? EMF is the voltage that you will measure across the cell when the switch is open and no current is flowing. So let's switch this on. It's on voltage and it's reading 1,25 volts. Let's see if you can see that. 1,25 volts. Now that is the EMF. 1,25 volts, and that is with the switch open. Now let's close the switch. Look at the circuit. If I close that switch, what looks different to normal circuits? Do you notice that there's no resistance in the circuit? We are actually creating a thing called a short circuit. Means there's no resistance. So if it was a car battery, this would spark, but it's only a little battery. Let's see what the voltage does when we have a short circuit. So let's hope you can see that. Look at that. We short circuit it, and the voltage dives to 0.07. The lowest was 0.07 volts. So we call that the terminal potential difference when a current is flowing and when the switch is closed. So it differs from the EMF, that's your maximum. So our terminal potential difference with no external resistance, 0.07 volts. What is our resistance in the circuit? The ammeter has no resistance, so external resistance is 0. What is our internal resistance? We're trying to find it. Now we've got to set this up and use this as an ammeter. So we've got to take the voltmeter out. It makes no difference to the reading that we'll get on our ammeter, and let's do that. So we're going to first switch it off. Let's turn that onto the ammeter setting. We're going to need to put this here. We're taking these out, and I'm going to place, there's positive, there's our negative, and now we're ready to measure this. Now this is in fact a short circuit. Let's switch it on and measure the current. 0.87 amps. So with the switch open, there's no current. with the switch closed, 0.83 or 4 amps. Let's see if we can get this so that you can see it. 0. Now let's close it. 0.81 amps. I equals 81 amps. Now we have everything we need. Let's use this formula and calculate the internal resistance. So we're going to say EMF equals IR plus I little r. We know the EMF, we measured it at 1,25 equals I, we measured 0.81, 0,81 times, there was no external resistance, plus I 0,81 times R. So 1,25 equals 0 plus 0,81 R. Dividing both sides by 0,81, that cancels out and leaves us with R. And so internal resistance is 1.25 divided by 0.81 equals 1,543. So that's 1,54 ohms. Now, how easy was that? In school, sometimes this can take us one lesson or dozens of lessons. I'm not saying that this is the most perfect method, but I'm saying I've never thought of doing it this way before, and it seems to give us an answer, and it uses the correct formula and ticks most of the boxes, so there it is.